Bond villain layers to Superman's fortress of Solitude, ice bases have always captured our imagination. But what Hollywood got wrong was thinking they were impossible to build. In reality, by 1960, the U.S. Army had begun Camp Century, a 3-kilometer pilot test under the ice housing 200 men beneath Greenland's ice cap. The official story, scientific research. The truth. Camp Century was just the beginning of a plan so audacious it could have changed the Cold War forever. The full Project Iceworm envisioned a 130,000 square kilometer complex, 3 times larger than Denmark. Now, with 2025 bringing unprecedented Arctic military activity, with Russia and China modernizing ice bases again, this buried secret is more relevant than ever. The scale of what America actually planned was staggering. The nuclear-powered city under ice. What the Army envisioned was an underground city stretching across an area 3 times larger than Denmark, carved directly into the Greenland ice cap. Not some modest research station, but a sprawling metropolis designed to house 11,000 military personnel in 4,000 kilometers of interconnected tunnels. Project Iceworm represented the most ambitious construction project ever attempted in polar conditions, dwarfing anything built before or since in the Arctic. The Army's vision went far beyond a simple military base. They planned to create a complete self-sustaining civilization beneath the ice, complete with residential quarters, dining facilities, recreation centers, medical clinics, and workshops. The underground city would feature its own power grid, water treatment systems, waste management facilities, and communication networks. Engineers designed living spaces that could accommodate families, complete with schools for children and shopping areas for daily necessities. The facility would include theaters for entertainment, gyms for fitness, and even churches for worship services. Creating such a massive installation in one of Earth's most hostile environments required revolutionary engineering approaches. The temperature regularly dropped to minus 40 degrees Celsius, with howling winds that could reach 200 kilometers per hour. The ice cap itself presented unique challenges, constantly shifting and moving under its own immense weight. Traditional construction methods would prove useless in these conditions, forcing engineers to develop entirely new techniques for excavation, construction, and maintenance in frozen environments. The power requirements for this underground metropolis demanded an unprecedented solution. Diesel generators could never supply the massive energy needs of 11,000 residents and their equipment. The Army decided to install a portable nuclear reactor specifically designed for Arctic conditions. The PM-2A reactor would generate enough electricity to power a medium-sized city, providing heating, lighting, and power for all the sophisticated equipment needed to maintain operation. This reactor represented cutting-edge technology, engineered to operate reliably in extreme cold while providing continuous power for years without refueling. Construction techniques had to be invented from scratch. Engineers developed specialized snow removal equipment capable of carving through hundreds of tons of packed ice per hour. They designed prefabricated tunnel sections that could be assembled in Arctic conditions, using materials that wouldn't become brittle in extreme cold. The tunnels themselves required innovative arch designs to distribute the enormous weight of ice above, while flexible joints allowed for natural ice movement without structural failure. The project operated under extraordinary secrecy measures. Officially, the Army described their work as peaceful scientific research into Arctic construction methods and climate studies. They established Camp Century as a smaller demonstration facility, housing just 200 personnel to test construction techniques and living conditions. The public story emphasized international cooperation and scientific advancement, with researchers from multiple countries participating in studies of ice core samples and weather patterns. Behind this peaceful facade lay a military purpose so significant it justified spending billions of dollars in 1960s money. Greenland's strategic position provided unprecedented advantages for nuclear operations. Located between the United States and Soviet Union, missiles launched from the ice cap could reach Moscow faster than weapons fired from American soil. The massive ice sheet offered natural camouflage that would make detection virtually impossible, even with advanced reconnaissance satellites. The extreme environment itself provided protection, as few Soviet agents could operate effectively in Arctic conditions for extended periods. The true purpose of Project Iceworm involved creating the ultimate hidden fortress for America's most powerful weapons. The underground city would serve as a mobile missile base, constantly shuffling nuclear weapons between different launch sites to prevent Soviet targeting. The facility would house hundreds of specially modified intercontinental ballistic missiles, each capable of delivering multi-megaton warheads to targets across the Soviet Union. Command and control systems, buried deep in the ice, would coordinate launches and maintain communication with Pentagon leadership. The defensive advantages were equally impressive. The massive ice cap provided natural armor several hundred meters thick, requiring direct hits from the most powerful nuclear weapons to penetrate. The distributed tunnel system meant that even multiple nuclear strikes couldn't destroy the entire facility. Soviet war planners would need to target thousands of potential launch sites scattered across an area larger than most European countries, requiring them to expend their entire nuclear arsenal just to attempt eliminating this single installation. Intelligence estimates suggested the Soviets would need over 3,000 nuclear missiles to guarantee destruction of the Iceworm complex, far more than their existing arsenal could provide. This created an impossible strategic equation where attacking the facility would consume so many Soviet weapons that they couldn't simultaneously target American cities and military bases. The underground city would survive any conceivable first strike, while retaining the ability to devastate the Soviet Union in retaliation. But understanding why the Pentagon was willing to invest so heavily in this frozen fortress requires examining the nuclear predicament that haunted military planners throughout the 1950s. Cold War nuclear strategy revolution. The nuclear age created a terrifying vulnerability that transformed military strategy. America's growing arsenal of atomic weapons sat exposed at known locations, making them perfect targets for a Soviet first strike. Strategic Air Command bases housing nuclear bombers were clearly marked on maps and easily identified from satellite reconnaissance. The massive B-52 stratofortresses required long runways and extensive ground support facilities that couldn't be hidden or disguised. Enemy planners knew exactly where to aim their own nuclear weapons to eliminate American striking power before it could respond. The situation grew worse as both superpowers developed intercontinental ballistic missiles. The first generation of American ICBMs like Atlas and Titan required enormous launch complexes with above-ground fuel storage tanks, guidance systems, and support buildings. These installations were visible from space and took hours to prepare for launch. Soviet reconnaissance satellites could easily count American missiles and target each installation individually. The Jupiter and Thor medium-range ballistic missiles presented even greater vulnerabilities. Stationed at exposed bases in Turkey, Italy, and Britain, where they served as obvious targets for Soviet retaliation. These shorter-range missiles created additional strategic problems because they needed positioning close to Soviet borders to reach their targets. The Jupiter missiles in Turkey could strike Moscow in just 10 minutes, making them incredibly threatening to Soviet leadership, but equally vulnerable to conventional attacks or sabotage. The weapons required large crews for maintenance and operation, complex ground support equipment, and regular fuel deliveries that made concealment impossible. Any conflict would likely begin with coordinated strikes against these exposed installations, eliminating much of America's nuclear capability before the weapons could be used. The Cuban Missile Crisis demonstrated just how dangerous this vulnerability had become. Soviet medium-range missiles in Cuba could have destroyed strategic air command bases across the southeastern United States within minutes of launch. The crisis revealed that both superpowers had created nuclear forces that were powerful but fragile, capable of devastating attacks, but unable to survive an enemy first strike. Military analysts calculated that a coordinated Soviet attack could eliminate 80% of American nuclear forces before they could respond, leaving the United States defenseless against follow-up strikes on cities and industrial centers. Pentagon strategists explored various solutions to protect American nuclear forces from surprise attack. Operation Chrome Dome kept nuclear-armed B-52 bombers airborne around the clock, ensuring that some weapons would survive any ground attack. These airborne alert missions required enormous resources and created constant safety risks. including several accidents that nearly triggered nuclear detonation. The program consumed vast amounts of fuel and required hundreds of aircrews to maintain continuous coverage, making it extremely expensive and difficult to sustain long-term. Engineers developed hardened missile silos designed to withstand nuclear attacks, burying Minuteman ICBMs in reinforced concrete bunkers scattered across the American Midwest. These underground installations provided better protection than surface facilities, but remained vulnerable to direct hits from accurate Soviet warheads. The silos' fixed locations meant that enemy planners could target each installation individually with multiple warheads to ensure destruction. Satellite reconnaissance made it impossible to hide new silo construction, giving the Soviets complete knowledge of American missile locations and quantity. Military planners began considering more radical approaches to the survivability problem. What if nuclear weapons could be hidden in locations so remote and inhospitable that enemies would never think to look for them? The concept required finding terrain that provided natural camouflage while remaining accessible to American forces, but not Soviet reconnaissance. The location would need to support large-scale military operations while maintaining complete secrecy from enemy intelligence services. Greenland emerged as the perfect solution to America's nuclear vulnerability crisis. The massive ice sheet covered 1.7 million square kilometers, providing unlimited space for concealed installations. The island's position between North America and Europe placed it closer to Soviet targets than missile bases in the continental United States, reducing flight times and increasing accuracy. Denmark had granted the United States military access rights during World War II, giving American forces legal authority to operate on Greenlandic territory without requiring additional negotiations. The ice cap offered natural advantages that no other location could match. Satellite reconnaissance would see only unbroken white expanses with no visible signs of military activity. The extreme climate deterred Soviet intelligence operations and made infiltration by enemy agents nearly impossible. The constantly shifting snow would bury any surface traces of construction within months, creating perfect camouflage that renewed itself automatically. Enemy planners would face the impossible task of targeting weapons they couldn't locate or even confirm existed. Traditional missile silos concentrated nuclear weapons in predictable patterns that simplified enemy targeting calculations. An ice-based installation could scatter launch sites across thousands of square kilometers, forcing Soviet planners to allocate multiple warheads for each potential location. The mobile nature of ice tunnel systems meant that missiles could be moved regularly between different launch points, making accurate targeting impossible even with perfect intelligence. The strategic mathematics were compelling for American war planners. A hidden ice base would shift the strategic balance by creating an undetectable nuclear arsenal that could survive any first strike. But creating such a revolutionary weapons system would require missiles specifically designed for the unique challenges of Arctic deployment. The Iceman missiles, developing weapons for these conditions, demanded completely new engineering approaches. The Army needed missiles specifically engineered for Arctic deployment and mobile operations. Standard ICBMs like the Atlas and Titan required massive launch complexes with above-ground fuel systems that would freeze solid in Greenland temperature. The propellants used in conventional missiles turned into useless slush at -40 degrees Celsius, while electronic components failed when exposed to extreme cold and constant moisture from melting ice. The solution emerged from Chrysler Corporation's missile division, which developed specialized weapons designated as Iceman missiles. These weren't entirely new designs, but heavily modified versions of the Minuteman ICBM, redesigned from the ground up for Arctic conditions. Engineers replaced standard fuel systems with solid propellants that remained stable in extreme cold, while new heating systems kept critical components at operational temperature. The missile bodies received special coatings to prevent ice buildup on control surfaces, and guidance systems incorporated Arctic-specific navigation corrections to account for magnetic field variations near the North Pole. Each Iceman missile carried a single thermonuclear warhead with a yield of 2.3 megatons, roughly 150 times more powerful than the bomb dropped on Hiroshima. The weapons measured 18 meters in length and weighed approximately 35 tons when fully fueled and armed. Their range extended to 5,000 kilometers, sufficient to reach any target within the Soviet Union from Greenland launch sites. The warheads incorporated the latest fusion bomb technology, using lithium deuteride as fusion fuel and a plutonium fission trigger to achieve maximum destructive yield while maintaining compact dimensions suitable for ICBM delivery. The revolutionary aspect of the Iceman system wasn't the missiles themselves, but their deployment concept. Rather than fixed silos, the weapons would operate from a mobile rail network that could shuffle missiles between launch sites to prevent Soviet targeting. Military planners designed a system using 600 missiles distributed among 2,100 potential launch positions scattered across the ice cap. The missiles would move constantly between different locations, with Soviet intelligence never knowing which sites actually contained active weapons versus empty decoys. Rail lines would crisscross the ice cap in a grid pattern covering the massive area. The network required over 4,000 kilometers of track, constructed using special steel alloys that remained flexible in extreme cold. Mobile launch cars would transport missiles between different tunnel sections, stopping at hardened launch silos that could be activated within minutes of receiving fire orders. The entire system operated like a massive shell game, with weapons constantly relocating to prevent enemy forces from developing accurate targeting information. This mobile deployment created a psychological warfare advantage that went beyond simple camouflage. Soviet war planners would face an impossible calculation when trying to eliminate the Iceman threat. Intelligence services might identify 2,100 potential launch sites, but would never know which ones contained actual missiles at any given time. The constant movement meant that targeting information became outdated within hours, forcing Soviet forces to attack far more sites than necessary to ensure hitting mobile weapons that might have already relocated. The technical challenges of maintaining missiles in Arctic conditions required numerous engineering innovations. Each launch site needed heating systems to keep weapons at operational temperatures, while moisture control systems prevented ice formation on critical components. Maintenance crews would work in underground facilities connected to the tunnel network, performing regular inspections and repairs without exposing missiles to surface conditions. Special transport vehicles would carry replacement parts and technicians throughout the tunnel system, maintaining operational readiness across the entire network. Command and control systems for coordinating 600 mobile missiles required technology that pushed the limits of 1960s capabilities. Underground command centers would track the location of every missile in real time, maintaining communication with mobile launch crews and Pentagon leadership. The system needed redundant communication links to ensure that launch orders could reach weapons even if primary communication lines were damaged by enemy action. Computer systems would calculate optimal launch sequences and target assignments, accounting for missile locations and flight paths to maximize destructive effectiveness. The coordination complexity was staggering. Launch commanders would need to track which sites contained missiles, which were empty decoys, and which were undergoing maintenance or relocation. The system required precise timing to ensure that missiles didn't collide during simultaneous launches from nearby sites. Weather monitoring systems would track wind patterns and visibility conditions that could affect launch operations, while navigation systems would provide updated targeting coordinates accounting for ice movement and magnetic field variation. The strategic mathematics worked heavily in America's favor. Soviet forces would need to attack thousands of potential launch sites to ensure eliminating the mobile missile threat. Intelligence estimates suggested that neutralizing the Iceman system would require over 3,500 Soviet nuclear warheads, far exceeding their existing arsenal. This created an impossible strategic equation where attacking Greenland would consume so many Soviet weapons that they couldn't simultaneously target American cities and military installations. The mobile launch system would have fundamentally altered Cold War nuclear dynamics by creating an undetectable and essentially invulnerable nuclear force. But first, The Army had to prove that such an ambitious underground complex could actually be built in one of Earth's most hostile environments. Building the impossible. Camp Century became the testing ground where theory met Arctic reality. Carving a massive underground complex through solid glacier ice sounds like something from a fever dream, but Army engineers approached this challenge with methodical precision. The Greenland ice cap presented conditions unlike anything encountered in conventional construction projects. Temperatures regularly dropped to -57 degrees Celsius, while howling winds reached speeds that could knock grown men off their feet. The ice itself wasn't uniform, but contained layers of different densities, air pockets, and hidden crevasses that could swallow entire vehicles without warning. The Army developed specialized excavation equipment specifically for ice removal operations. The Swiss-manufactured Peter Snowmiller became the workhorse of tunnel construction, capable of chewing through 120 cubic meters of packed snow and ice per hour. This massive machine operated like a mechanical beast, with rotating cutting heads that pulverized ice into manageable chunks while conveyor systems transported debris away from work area. The miller required constant maintenance in Arctic conditions, with crews working around the clock to prevent hydraulic fluid from freezing and metal components from becoming brittle in extreme cold. Construction crews discovered that traditional building techniques were useless in ice environments. Standard concrete cracked immediately when exposed to temperature fluctuations, while steel became so brittle it shattered under normal working loads. Engineers developed innovative arch-shaped tunnel designs that distributed the enormous weight of ice overhead while allowing for natural expansion and contraction. The tunnels measured 8 meters wide and 4 meters high, providing adequate space for vehicle traffic and equipment installation, while maintaining structural integrity under hundreds of tons of ice pressure. The sealing systems required revolutionary approaches to prevent collapse while allowing for ice movement. Engineers installed corrugated metal panels that could flex with natural ice shifts without losing structural strength. These panels were heated continuously to prevent ice buildup that could add dangerous weight loads. Insulation systems kept interior temperatures comfortable for personnel while preventing heat loss that could destabilize surrounding ice formation. Getting construction materials and equipment to work sites hundreds of kilometers from the nearest port created logistical nightmares that tested military planning capabilities. Every piece of equipment, every construction component, and every supply item had to be transported across the ice cap using specialized vehicles designed for Arctic conditions. The Army established Camp Tudo as a coastal staging area where ships could unload cargo during the brief summer months when ice conditions permitted maritime access. The supply system relied on heavy sled trains pulled by massive tracked vehicles that could navigate across ice fields carrying enormous loads. These convoys operated like Arctic freight trains, with multiple cargo sleds connected in sequences that stretched for hundreds of meters. The tracked vehicles consumed enormous quantities of fuel while battling through snowdrifts and around crevasses that appeared without warning. Working conditions challenged every aspect of conventional construction practices. Metal tools became so cold they could freeze to exposed skin within seconds, requiring workers to wear special gloves and use heated tool storage systems. Welding operations required enclosed heating tents to prevent metal from cooling too rapidly and developing stress fracture. Electronic equipment failed regularly when moisture condensed on circuit boards and froze into ice crystals that caused short circuits and component failure. The extreme temperatures created constant equipment failures that slowed construction progress. Hydraulic systems required special Arctic-grade fluids that remained liquid at -40 degrees, while engines needed continuous heating to prevent fuel lines from freezing. Battery-powered equipment lost most of its capacity in cold conditions, requiring heated storage areas and frequent recharging cycles. Supporting thousands of personnel in such hostile conditions required sophisticated life support systems that went far beyond basic heating and shelter. The underground facility needed massive ventilation systems to provide fresh air while removing carbon dioxide and moisture that could create dangerous conditions. Water supply presented unique challenges since conventional wells were impossible in frozen ground. Engineers developed the Rodriguez well system, which used heated probes to melt ice and create water sources directly from the glacier itself. Power generation for such a massive facility eliminated conventional diesel generators as practical options. The fuel requirements alone would have demanded constant supply convoys that were vulnerable to weather disruptions. The nuclear reactor solution provided reliable power generation that could operate continuously without fuel resupply, while generating enough electricity to support heating, lighting, and equipment operations for thousands of personnel. The PM-2A reactor represented cutting-edge portable nuclear technology designed specifically for remote installations. The reactor core contained 20 kilograms of highly enriched uranium that could generate 2 megawatts of continuous electrical power for years without refueling. The entire reactor system weighed 400 tons and required specialized transportation equipment to move components across the ice cap to installation site. Camp Century proved that large-scale ice construction was not only feasible, but could create surprisingly comfortable living conditions in the world's most hostile environment.